Okay, this is hints and tips for number 8 on the 3D worksheet. World's largest flower pot is 1.595 meters high. If you were to jump horizontally from the edge of the flower pot with a speed of 3.0 meters per second, what's your landing velocity? So that first picture, the flower pot, because it's a weird question, let's draw the picture. VI is 3.0 meters per second. That's all on the x-axis because the jump is horizontal. And we're looking for VF. Now that is VF total. So if you notice the little picture over on the other side where I've labeled VFY, VFX, and VF total. Don't forget that VF total is the resultant vector of the VFY and VFX. So we could find VF total by using good old Pythagoras. VF total equals VFX squared plus VFY squared, square root thereof. Well, problem is we don't have those, do we? So let's list the variables that we're aware of. I've created the table for x and y variables. I've listed my initial velocities. VIX is 3.0 meters per second. VIY is 0. Now, when I go to acceleration, I know that acceleration on the x-axis is 0, and because of that, VFX is also 3.0 meters per second, which means I have one of the pieces to use Pythagoras to find the total final velocity. I know that acceleration on the y-axis is gravity, negative g, and I don't know the VFY, but this is a case where I do know the y displacement, negative 1.5 meters. So I can treat this as a free fall problem and analyze the motion on the y-axis separately. I can do VFY squared equals VIY squared plus 2a delta y. And of course, because VIY was 0, that cancels out, and I end up with VFY equals the square root of 2a delta y. I can plug that in and I get a VFY of 6.185 meters per second, and a whole bunch of pocket change. So I can go ahead and set this up. I'm plugging that value that I got for VFY into Pythagoras for the final y velocity, squaring it. And I end up with VF total being the square root of 47 and change. I get a VF total of 6.8745. Note that my answer rounds differently than the book's answer because I'm more careful with not rounding in intermediate steps than they are. So it should round to 6.87 meters per second. Now you still have to have that angle theta, and note that that is marked in red on the little triangle that I drew over on the side there. Tangent of theta is equal to the opposite over adjacent, the VFX over the VFY. That gives me that interior theta. So the inverse tangent of VFX over VFY would give me theta. Now the book gives the answer for the theta out here. It gives the angle below the horizontal. You are welcome to do that. If you were flipping these, then the opposite would be VFY and the adjacent would be VFX, because we can always move vectors parallel to themselves. So either way you do it, just make sure that your description is correct. If you're using the red theta that I have figured for here, I would give the angle as out from the flower pot. If you're using the purple theta that the book gives, then below the horizontal would be an appropriate description. That's it.